Yeah, so now that you remember that conversation, I made this cryptic remark about how they should lie on a hexagon in the complex plane, and presumably at the time that didn't make any sense, but I said eventually it would make sense. So in this problem, it is going to make sense. So the statement of the problem is to find all complex solutions. So we're going to find all solutions to this equation, including ones which are complex numbers, and the equation is x raised to the power n equals 1, where n is some integer. So for example, there's an easy case, like if n equals 2, then what are the two solutions to x squared equals 1?
1 and -1?
Yeah, 1 and -1. So in that case, it's pretty easy. I'll just maybe I'll just draw those to start getting us intuition for the way this is going to look in the complex plane. So you remember what the complex plane is, right? This is the thing where the y-axis is I and the x-axis is 1, the real part. Is this ringing bells?
Yeah.
Okay, good. So the two solutions that you just told me are plus and minus 1. So here's the plus 1, and here's the minus 1. Okay. So I'm going to skip 3, n equals 3, because it's slightly trickier. But can you see well, first of all, when n equals 4, we're trying to solve the equation x to the power 4 equals 1. How many separate solutions, just based on the general rules for polynomials, how many solutions do you expect this to have?
I'd say 4.
Yeah, this should have 4, unless there's some weird multiplicity thing. So there should be 4 solutions. I think you can tell me at least 2 of them right away without thinking very hard.
There's 1 and -1.
Good, okay. So 1 and -1 are nice because they both square to 1. Those certainly work. But here we're raising x to the 4th power, so there should also be solutions where x squared is -1, because then if x squared is -1, why do I keep trying to change color and it's not working? There we go. Yeah, so you told me 1 and -1 work, which is true, because 1 to the power 4 is +1, and -1 to the power 4 is +1. But I think there should be 2 more solutions that square to -1, because if they square to -1, -1 squared is +1. So what other solutions do you think this equation could have?
Plus and minus I.
Yeah, I and minus I. So I to the 4th is 1, and minus I to the 4th is 1. Okay, so now we're starting to see a pattern, because if you kind of think of putting in this unit circle we've been doing from trigonometry, so if you put in this unit circle, and that's not going to be a circle, you put in, that looks like an oval now, whatever. If you put in the unit circle, the n equals 2 solution has these 2 points that are evenly spaced along the circle, right? They're at 0 degrees and pi. Well, 0 and pi, or 0 and 180 degrees. N equals 4, they're at 0, 90 degrees, 180, and 270, or 0 pi over 4 pi and 3 pi over 4. So they're evenly spaced. So if you connect them, if you connect those 4 points that you just told me for the n equals 4 case, they form, what is it, a square inside the circle, right? Which I'm drawing increasingly poorly. Yeah, that looks like a parallelogram, but whatever. So we're starting to see that the solutions for any n are going to lie on the vertices of a regular n-gon. Oh, that's unfortunate. Looks like I wrote stuff on that slide last week. So now we're going to try... where do I go? Alright, I'm just going to erase this one. Do you have thoughts or questions on this so far while I erase?
Nope.
Okay. Well, then there's just going to be a few seconds of awkward silence while I try to get the right... There we go. It has to be 2.96 precisely. I like that number.
I like the included carrying case in this with this tablet. It's so greatly built. So greatly.
Do you think you're actually ever going to use a carrying case to take it somewhere?
No.
Yeah, me neither. Okay, so we've done a bit of exploration, so now let's try to solve this in general. So we're going to solve x to the n equals 1, and I'll give you a hint for the ansatz. So we're going to start, since we're going to look for complex solutions, so since you're taking German, do you know this word Ansatz? A-N-S-A-T-Z?
I don't believe I do. It kind of sounds like another word for a pause.
Ah, okay. I don't actually know what this means in German, but in math you often use this word for a guess. If you have a guess for what the solution is going to look like, you try the guess and then check whether it works, and that strategy is called using an Ansatz. And apparently Ansatz is a German word, but I don't know what it means in German, so I just think of it as a guess. But alright, so we're going to make the guess. Suppose x can be written as some complex number form, like this e to the I theta, right? And that guess is just based on the two examples we saw above, right? Because, for instance, in the n equals 4 case, the solutions were 1i minus 1 minus I, which are exactly e to the I0, e to the I pi over 4, or sorry, e to the I pi over 2, and e to the I pi, and e to the I 3 pi over 2. So finally, I'll ask you, if I make that substitution, what does the equation become?
The equation would become, I believe, wait. Well, it would become e to the power of ni theta. That's just a total guess.
Yeah, and how did you simplify to get ni theta in the exponent?
I kind of just added an onto the I theta. I didn't know what I was doing.
Okay, I mean, it's correct, but we should be a little careful about why that's true, because all I did was take x equals e to the I theta and plug it into the equation, but then the reason that this simplifies is because power to a power, right? So,
yeah, okay.
Good. Okay. Now, we can rewrite this using Euler's formula, so in terms of cosines and sines, what do I get next?
I should probably start memorizing his formula. Well, the various formulas, just so that I have an idea what's going on.
Yeah, the consolidation document will make you write definitions of a lot of things, so you might be unhappy, but then it will be easier to remember them. I can give you a trick to remember it if you want, because, I mean, if I'm being honest, I don't memorize anything. I just re-triangulate definitions based on other stuff that I know, right? I always try to figure stuff out on the fly rather than memorizing. So if you're asking what is e to the I n theta or e to the I x for anything, I just think about the complex plane. So that's the one where there's 1 and I. And I know that e to the I thing is labeling some point on that circle in the complex plane. So this is almost like the unit circle x and y, except now y is complex. So if this number that I'm labeling is e to the I theta, then in Cartesian coordinates, the x and y coordinates are cosine theta and I times sine of theta, right? Because sine of theta is the y coordinate, but here we're thinking of it as the complex plane. So if you always think about that circle, and just remember e to the I theta is giving you a point on the circle, and that's related to trigonometry because sine and cosine give you the x and y coordinates, you'll always remember e to the I theta is cosine theta, because the real part is the x, plus I sine theta, because in the complex plane, y is the imaginary part.
So would cosine theta plus I sine theta in this scenario, would what we just got be e to the power I n theta equals cosine theta plus I sine theta to the power of n? That's a total guess.
It is, yeah, so that's true. You can write it that way as, since that's like taking this side of the equation, right? That's like putting cosine theta plus I sine theta inside the parentheses, then raising it to the power n. So that's true. That is one way to write it. I claim that there's an easier way to write it because we don't want to raise things to the nth power because foiling n times is hard. It's easier to use the right side and just apply the formula replacing theta with n theta, right? See what I'm saying? Because the equation I've written in green here is true for any value of theta. So in particular, we can apply it for n theta. So if we do that, what should I write?
So that would be e to the power of I sine theta equals cosine n theta plus I sine n theta.
Good. And that's all equal to 1, right, from the previous line. I
Yes.
sine n theta. Okay, well that's pretty easy to figure out because now we just use this trick. This is a complex equation, right? So I'm going to write the right side a little more suggestively. 1 is 1 plus 0 times I, right? So what's the rule that we remember whenever you have a complex equation? You get 2 equations out of it for free. What are those 2 equations in this case?
I believe in this case it would be 1 plus 0 I and 1 minus 0 I.
1 plus... Well, those are both 1. 1 plus 0i and 1 minus 0i, you're saying. I think what we want to do is set the real part of the left and right sides equal, and also set the imaginary parts equal. Right, because this is... The left side has this real part, cosine n theta, that's a real number. And then it has I times sine of n theta, that's the imaginary part. And the right side has the real part, 1, and the imaginary part, 0. And the only way 2 complex numbers can be equal is if their real and imaginary parts are separately equal. So if we use that, setting the real and imaginary parts equal, what data...
Oh, I see what you mean now. That took me quite a while.
Yeah, that's fine. What data do we have then?
Okay, this is going to be another total guess. I believe that we can set cosine n theta equals 1.
Yeah.
And also I sine theta, I sine n theta equals 0i.
Yeah, so I'll just divide by I in that second equation, because there's a 0 on the other side, so that tells us sine n theta equals 0. Okay. So now we have to do that thing that we saw, I think in the previous meeting or 2 meetings ago, where there's these wraparound solutions, right? Because we know there should be n possible solutions to this equation, say cosine n theta equals 1. So one of those solutions we can write down very easily, because we know cosine of 0 equals 1. So this equation is certainly solved if theta is 0, right? Because if theta equals 0, I plug in cosine of n times 0 is 0, and cosine of 0 equals 1. Another solution is if you wrap around all the way to 2 pi inside, right? Because cosine of 2 pi is the same as cosine of 0, that's 1. So I'll ask you, what value of theta would give me cosine of 2 pi inside this argument?
I believe that, wait, give me a sec. Wouldn't that just be 2 pi? I don't know what you're asking.
So I'm saying, what value of theta would have the property that the argument, which is n times theta, is equal to 2 pi?
I'm gonna guess pi. Oh, I see what you're doing here.
Yeah, because we know, maybe I should write it more explicitly. So we know cosine of, maybe I'll go over here. So that was something else. Well, whatever. So we know cosine of 2 pi is the same as cosine of 0, which is 1. And we're trying to solve the equation cosine of n theta equals 1. So the top thing is what we know. So we know the bottom equation will be solved if n times theta equals 2 pi. And what I was asking is what value of theta makes that true? Well, I think we can solve for theta pretty easily to get theta's 2 pi divided by n, right?
Oh, okay.
Good. Okay, so theta can be 0. It can be 2 pi over n. Maybe you see the pattern now. What other solutions do we have? Continuing the pattern, the first one came from setting n theta equal to 0. The second one came from setting n theta equal to 2 pi. What are the remaining solutions?
So I believe it would be 4 pi over n, 6 pi over n, etc.
Yeah, it goes 4 pi over n, ... And then this stops once we reach, I guess, n pi, or yeah, I guess it's it depends on what n is, how far we can go. If n is 5, for instance, then we would want to go up to, what, 10 pi over 5, which is 2 pi, right? So we end when we reach theta equals 2 pi, because that would be 0. So it should, the last one I think should be 2, let's see if I can get this right, 2 times n minus 1 pi over n, is that right? Then the next one would be 2n pi over n, which is 2 pi. I think that's right. So how many solutions do we have? Well, we have 1, 2, 3, up to n minus 1. So there's n solutions here, plus the 0 solution, which gives us n total. So the counting works out. This is good. Now you could just ask, what do those n different points look like in the complex plane? Well, that's not the color I want. Man, this is very bad erasing, so now it's looking gray. Well, what they look like is, since they're all evenly spaced, we saw that the difference, they're like 2 pi over n, 4 pi over n, and so forth, so the difference between all of them is 2 pi over n. 2 pi is 360 degrees, so we're really just splitting the entire circle, which is 360 degrees, into n evenly spaced points, and distributing the solutions to this equation along, well, I can't draw very well, but distributing it in an even way along the circle. So for instance, if there's 8 of them, we have one solution which is 0, let's see, 2n pi over 8, or sorry, 2 pi over 8 is the same as pi over 4, right? So pi over 4 is this. Then 4 pi over 8 is pi over 2. 6 pi over 8 is 3 pi over 4. 8 pi over 8 is pi. 10 pi over 8 is down here. 12 pi over 8. Yeah, I think this works, right? So these are the points of, so this is n equals 8. N equals 8. Just writing down each of those points. So for instance, this is 2 pi over 8. Just listing those things you told me, 2 pi over 8. So you can see these form the vertices of an octagon in the complex plane if you connected all of these. So the punchline of this...
So,
sorry, go on.
Is this implying that you can graph points on a complex plane effectively in a Cartesian way?
Yeah, I think...
I mean, not Cartesian.
You mean polar?
Yeah, polar.
Yes.
That was...
You could do it in either way, is the point. We could do, I guess, the way you probably did it in algebra was x plus iy. So maybe someone told you a point like, I don't know, 2 plus 3i, and what you did was go 2 to the right and then 3 up and plot that point. Is that what you did?
Yeah. This is... I think I'm understanding what you're doing here, though.
Yeah, because here we're doing something slightly different, which is instead of giving you x and y, I'm saying I could label points. I mean, we could also have a radial coordinate, r and theta, and then the complex number would be written like this, r e to the I theta would be the complex number z. So all we're doing is using the complex coordinates we saw a couple meetings ago, r and theta, for complex numbers, and using Euler's identity to convert it to trigonometry.
That's cool.
Yeah, I think I botched the explanation a little bit, but thoughts or questions on this?
I have no questions. I like where this is going.
Okay, good. As long as you, 1, remember Euler's formula, and 2, could follow this step where we got all these wraparound solutions. I think that's important. Good. What else do I have? Ah, yes. Okay. I wanted to talk about this again.
But did we really finish the previous one, or you just... Because the original thing... Oh, wait. We did. Okay. I'm thinking of the one, as you said way back with the, well, x to 6 equals 1.
With the...
I don't know what I'm saying.
Were you asking if we solved this original question, x to the n equals 1?
Just curious if thinking.
Yeah, I should write the answer a little more clearly.
Yeah, it suggested showing off the hexagon that forms when you do x to the 6th equals 1.
Yeah, okay, yeah, maybe I should come back and make that part clearer. So we found the answer. Let me delete this, erase this too. So we found the answer, and now let's just check that the answer reduces to the hexagon thing that I said before. So this is tedious erasing. Good. So yeah, I think I tried the octagon for some reason, but I shouldn't have done that. So yeah, let's bring it back to x to the 6th equals 1. This was the thing that you were factoring before. So what if we just run through all of the steps in the solution we just gave for x to the 6th equals 1? Well, we made the ansatz x equals e to the I theta. So this was just a rewriting, defining your own variable, if you will. We're defining theta this way. So if you do that, we had e to the 6I theta equals 1. We found 6 solutions. Now they're solutions for theta instead of solutions for x. The 6 solutions are theta are 0, 2 pi over 6, which I think you told me, 4 pi over 6, and then I'll skip a few because then we go all the way up to 10 pi over 6. So we solved the equation because we've written, if you just plug in those 6 values for theta up here, you get 6 answers, but maybe those answers don't really mean much to you because they're written in e to the I theta notation, but we can make that better by just saying, well, e to the I theta is cosine theta plus I sine theta, so all we have to do is go on the unit circle in the complex plane by these 6 angles and plot those points. Well, that's pretty easy because 2 pi over 6 is pi over 3, which is maybe down here. 0 is even easier because it's, oh wait, sorry, that was pi over 6 I drew. Pi over 3 is up here. 0 is down here. 4 pi over 6, what's that? That's 2 pi over 3, which is down here, I think. Then the next one would be 8 pi over 6, which is 4 pi over 3. Wait, I have too many. Nah. This is pi over 3. 2 pi over 3. Then 8 pi over 6 would be 4 pi over 3. 0. I'm missing one. 1, 2, 3, 4. What am I missing? 6 pi over 6, which is pi. What am I doing? 6 pi over 6 is down here. Good. Alright, so pi over 3, 2 pi over 3, pi, 4 pi over 3, and 10 pi over 6 is 5 pi over 3. There we go. I'm just bad at doing arithmetic, but alright, so those are the 6 angles we found, and if you connect them, indeed, they are a regular hexagon. There we go.
Regular quotation marks.
Well, yeah, if you have a very generous definition of regular. Good. Okay, sorry. I notched that partway through. Are you at least convinced now that this solves the equation and that they are indeed on the hexagon?
Yes.
Okay, good. That's pi over 3. Okay, good. I wanted to make that deliver on my promise that eventually that would make sense. Okay, yeah, let's remember how inverse functions worked a little bit. So what are the domain and range, if you remember, of arcsine, which is sine inverse, arccosine, which is cosine inverse, and arctangent, which is tan inverse?
So each of these are inverse functions of sine, cos, and tan. So I'm gonna think about that.
Yeah. So you're saying this is sine inverse? I agree.
So the domain of arcsine would be 0 through -1, I believe, inclusive. and range would be zero and one.
Well, let's do the domain first. So you said 0 to 1, is that right?
Yes, inclusive.
Why 0 to 1?
Wait.
I think the domain of the inverse function should be the range of the original function.
Okay, yeah, I see what's going on here. So the domain of that would be the range of sine, which is -1 through 1 inclusive.
Good. Good. So now's the tricky part, because the ranges, remember when we defined these functions, they didn't have inverses to begin with. We had to restrict sine so they would have a good inverse, because sine fails the horizontal line test. So for the range, you have to remember how we restricted the range to get a function which passes the horizontal line test. So I will draw it quickly, but then ask you what the correct range is for arcsine.
So I believe that the range of arcsine would be, I'm going to say, wait, give me a sec. I believe that would no. Yes, -π/2 through π/2, inclusive again.
Perfect, yes. -π/2, π/2.
I almost said the same thing as before, 0 through π/2, because I was thinking that it can't be I wasn't thinking that, I just forgot that it can be.
Yeah, you have to be careful, because we do want negative values, because we need we need to chop up sine, in other words, so that you get all the values between -1 and 1, so it absolutely can be negative to get that chopping. Okay, good. Arc cosine. Ooh, there's actually an empty slide here.
Whoa.
Okay, so dom. Every time I write dom, I think of BDSM. Dom of arc cosine. I think the domain's pretty similar argument, right?
So I believe that the domain would once again be, give me a sec to think about this. This would be 0 through pi.
Is that the domain or the range of arc cos? I think what you just gave, you gave 0 to pi, so here's cosine. So here's pi. So this is cosine, and if we're talking about the domain of arc cosine, the domain of arc cosine is the range of cosine. And you said 0 to pi, which I think is the range of arc cosine. Is that what you meant? Or have I confused you? Wait, are you still there?
I'm here, I'm just thinking.
Ah, okay. I took a math project lab at MIT. They said there's two kinds of people. We had a communications workshop about how to talk about math with other people. And they said there's two kinds of people. There's some people that think to talk, which means they sit and think very quietly, and after they're done thinking, then they start talking. And the second type of people talk to think, where they need to say their stream of consciousness in order to think. So they just speak continuously. So it sounds like you're thinking to talk rather than talking to think.
Okay, I'm reasonably sure that the domain of arcsine is the interval -1 through 1 closed. Okay, This would be a closed interval, right?
Yes, because it hits those endpoints. So it includes -1 and 1.
Just check.
Good. What is the range of arc cosine then?
I'm probably thinking much harder than I really should be for this.
Yeah, let's just remind ourselves of how we did it for the arc sine a moment ago in the previous slide. So in that case we said, well, the domain had to be -1 to 1 because that's the domain of the inverse function should be the range of the original function, and the range of sine is -1 to 1. So that part of the argument goes through. Then we asked, well, how do we get the range of arc sine? And then we said, well, that has to be the chopping of sine into a region which achieves that domain. So we said, how could we chop up the sine function in such a way that it achieves the domain of -1 to 1 precisely once, so that it passes the horizontal line test? And then we just looked at the plot and said, well, if we chop it from -π/2 to π/2, then it hits every number between -1 and 1 precisely once, which is good. So now we want to generalize that to the cosine function, and the first thing we said is true, that the domain of arc cosine is still going to be -1 to 1. So now we just need to ask, how should you chop up the graph of cosine so that it hits every value between 1 and -1 exactly once?
I believe that this would be 0 through pi, since cosine is offset π/2 compared to sine.
Yeah, and in fact I even labeled this graph wrong. Good. So that number I wrote as pi was 2 pi. Very good. So yeah, because here's...
Wait. Okay, never mind.
Yeah, because cosine of pi is -1, right? I drew that wrong. So if we chop it like this, as you said, from 0 to pi, then we indeed hit all of the values from -1 to 1 exactly once, which is good. So now the only one that's different, what about this tangent inverse? So domain of arctangent, what should we do for that guy? Perhaps I will draw it for you.
I believe that this would also have a... Wait, no. This is a total guess. I believe that this would also have a closed interval, -1 to 1, as its domain. Inverse of tangent.
Well, here we should be careful because the domain of inverse tangent is the range of tangent. So what is the range? I've only drawn one part of it. But what is the range of tangent theta based on this graph? So the range is all the values it outputs, right? That's a bad graph. It certainly outputs values bigger than 1 and smaller than -1. So I don't think it can be -1 to 1.
So this would be π/2 and -π/2. Excuse me, swap that around, make it close, and that makes more sense. Since either... Wait, no.
Wait, are you telling me these 2 points, these asymptotes, are π/2 and -π/2?
Yes, and that is not in the domain since it is undefined, I believe.
It is undefined at this point, so that's good. What does that tell us? Okay, so I agree that if we restrict attention...
Oh my god, I'm dumb.
Yeah.
It's negative infinity to positive infinity.
Yeah, that's the domain of arctan, because that's the range of tan. Good. So if we hit all the real numbers because this thing blows up, goes to infinity or minus infinity. And then I think what you were about to say, what is the range of arctan then?
I'm reasonably sure that this would also be negative infinity through positive infinity.
Well, if we take minus infinity to positive infinity, then that means that we're keeping all of these values in the domain of tangent. And if we keep minus infinity to positive infinity, this thing fails the horizontal line test, right? Because it hits here. So we need a smaller range of arctan if we're going to pass the horizontal line test. So this is just like the cosine. In the cosine, this thing would have failed the horizontal line test if we kept the range of arccos to be minus infinity to infinity. So we said, all right, fine, we want to pass the horizontal line test, so we'll chop up the range of arccos so that it passes the horizontal line test. And we got from 0 to pi. So now we have to do a similar chopping of tangent to pass the horizontal line test. What chopping should we use here?
I believe that we should chop at the points that you've already marked, which would be negative pi over 2 and pi over 2.
Yeah, this time it's not inclusive, right? Because those two are not in the domain. Good, so these are open. Pi over 2, pi over 2. Good. Okay, I agree. So those are the domain and range of the inverse trig functions. So I think I've even asked you to write about this in the consolidation document because it's important to understand this. Yes, so question 2e, I even asked what are the ranges of the function arcsine and arccos and why are they different? So this is why they are different. You might have asked, sine and cosine look very similar. Why is it that the range of arcsine is minus pi over 2 to pi over 2, but the range of arccos is 0 to pi over 2? Now hopefully you can answer that question because you see the range comes from our choice of how to chop this function so it passes the horizontal line test, right? So we need different choppings for these two functions, which are shifted by pi over 2, in order to pass the horizontal line test. Okay, good. Thoughts or clarifying questions on this?
I don't believe I have any questions. I don't believe I have any questions.
Okay. Are you happy enough with that statement that you feel prepared to write an explanation of it for the consolidation document?
I believe
You are. You always hedge statements with belief, which is pretty good, I think. Okay. What else? Let me see what other questions there are. I think... Oh yeah, well that I turned into a question on the consolidation document. I can introduce it if you'd like. That's the hexagon thing. That's... Okay. Yeah, I guess I can introduce this because... or maybe... Yeah, maybe just for some quick drills, I will ask you... And you can even write these down if you want because you'll be rewriting them in a moment, but just to make sure you've been keeping up with all the reading and remembering things. So on the consolidation document, I'll ask you to state the definition of the number e as a limit. Do you remember that definition?
yes.
Good. What is that?
I believe that E can be expressed as the... Wait, should I just give effectively its equation?
Yeah, the equation defining e.
Okay. Keep thinking.
Pondering.
I believe it is 1 over... Excuse me. 1 minus n squared over n to the power of n. That's a lot of stuff in a single thing.
1 minus n squared over the power n, like that?
Yes.
To the power
of n, I think it was.
I think it's almost like this, but there's an overall minus, I think, because if these two signs are reversed, then I think as n goes to infinity, that one. How did you remember this? I never wrote the expression like this. How did you remember this fraction form of it? Curious.
Don't know.
Interesting. One. Oh wait, wasn't that right? Maybe this was the sign backwards. One. No. Yeah, it should be. The sign should be the other way. Good. Yeah, the way I remember it is, so yeah, this is e. The way I remember it is the limit as n goes to infinity of what is it? 1. Oh, maybe these are both plus. Yeah, sorry. I was trying to do algebra in my head and I was messing it up. 1 plus 1 over n to the power n. There we go. So you combine this and said, all right, I'm going to get a common denominator, and that's the same as, I guess, n over n, which would be n plus 1 over n. Okay, so it shouldn't be n squared, right? It should just be 1 plus n over n. I confused myself. Okay, so this is the limit definition of E, and as with most definitions, it's better not to actually memorize it. It's better to try to figure it out in real time. So where did we first see this? There was this daily challenge about the colony of bacteria growing, and the way that we came up with this E was to say that, well, there's going to be a fraction of them that divides in each period of time. So if in I don't know, you split the day into n segments, like 24 hours, and in each of those hours we had 1/24 of the bacteria divide, and then all of those double. So the thing on the inside is kind of the breaking up of bacteria into different groups, and then the power n is the number of times that you're multiplying by that factor. So this is the, I guess, reproduction factor or something for the colony of bacteria, when 1/n of them divide, and then they divide n times. And we were taking n to infinity. So if you forget it, you can kind of figure it out just from remembering the story about the bacteria. N to infinity. Okay. Questions on this?
No.
Still very interested in that, where the n squared thing came from. But, okay, good. Do you remember what the completeness property of the reals is?
There is, excuse me, let me think about this, because I know what it means, but I don't know how to work.
Good.
I guess the only way I can word it right now is that there's an infinite number of points between 2 points on.
So you're trying to rigorize the statement that the reals have no holes by saying there's infinitely many of them.
Yeah.
Okay, good. That's not quite enough, unfortunately, because it's also true for the set of rationals, right? If you have just the set of all, and I can't go over here because we use that for, okay, well, we'll move up by 1. So the set of rationals also have the property that if you take the set of all rationals between any 2 points, so if this is A and this is B, there's still infinitely many rational numbers in here. And I mean, one way to see that is that if A and B are rational, for instance, you can just take A plus B over 2, so you get the point halfway between, and then you take that midway point plus B over 2, and then you get another point here, another point here, another point here. You can get infinitely many rationals between those 2 points, but the rationals do not have a completeness property. So completeness has to be something different from infinitely many points between any two. There's a word for this. It's related to the word dense in mathematics. You say that a set is dense if any subset of the real line has infinitely many of the objects you're talking about. So good. That was a good attempt. You thought of the no holes and then tried to rigorize it, which is, I think, how you should produce definitions on the fly. But the completeness property is something slightly different. Completeness is that every subset a of the real numbers with an upper bound also has a least upper bound, or a supremum. Supremum. And of course the supremum has to belong to R as well. Okay, do you remember, is this definition ring bells now?
I do believe I recognize it.
Okay, good. So this is the precise definition of completeness that gives us no holes, because you asked on Slack once, is the supremum of a set of numbers of one type necessarily also of the same type? And I said no, because you could simply say, what is the set of all rationals such that the square of that rational is less than 2? So the supremum of this set is simply square root of 2. And then we see, well, all of these numbers are rational, but their supremum is irrational. So this is the reason that the rationals do not have a completeness property, because this set has an upper bound in the rationals, but it has no supremum in the rationals. The supremum exists in a different set. Okay, good. Somewhat abstract, but thoughts on this?
I have no questions or thoughts.
I have no thoughts. My brain is empty. Okay, what about these things that we remember? Do you remember now the definitions of all of these blackboard letters from last time? I will rewrite them.
I'm going to need to Google that, unfortunately.
Well, we can remember this. N, C. Well, which ones can you answer? I'm curious. Which ones can you answer without Googling? Which of them do you just recognize?
I believe that the blackboard R is the rational numbers.
R is reals, right?
Okay.
R for reals. So that's just, you can also write that as this number line, everything. Okay. What about this? So the mnemonic is R is for reals, Q is for quotient. So if Q is for quotient, which set is blackboard Q?
I don't know.
Okay. Yeah, quotients. A quotient is a thing divided by another thing. So this is all, A over B, where A, B here, and B is not 0. Right, so the set of all quotients is also known as the rational numbers, right?
Okay, so... Okay, I was going to say, isn't that just the rational set?
Yeah, it's good. Another mnemonic is that rational comes from the word ratio, and a ratio is a quotient of two numbers. Okay, good. What about these guys? Z from Zahl, the German for number. Do you remember what this one is?
I believe that Z is the counting numbers. 1, 2, 3, etc.
So that's N, the natural numbers.
Oh, natural number, okay.
Yeah.
So Z is -2, -1, 0, 1, 2, etc., I believe.
Yeah, I'll just write it in this kind of sloppy way, +or -1, +or -2, +or -3. Oh, I forgot 0, but I'll go out of order, +or -4, and ... Yeah, so good. So that's all the positive and negative integers is the word for this. Integers. Okay. And then what is C?
Don't remember this, so I'm just going to guess irrationals.
Not quite. So C is the complex numbers. So this is all like 1 plus 5i. So you can have imaginary numbers in here. You can have just I. X is in Y is in R. So C is the complex numbers. C is for complex. We don't actually have a symbol for irrational numbers. sometimes for irrational numbers I like to use blackboard I, but not everyone uses that. In linear algebra you sometimes write blackboard I for the identity operator, but not for the irrationals. So there's not really a good symbol for that. Okay, what other questions? Do you remember, can you explain the difference between the codomain of a function and the range of a function?
I don't believe I have a formal definition of these, but the codomain is effectively I'm going to say what range it operates on. So that would be one of the sets we just described. And the range is what values it outputs.
Yeah, right. Yeah, so the codomain is kind of just a matter of how you choose to write it, right? If you choose to write f from R to R, then this is the codomain. Or if you think of it as I do, as a function takes things in one set and then there's arrows between elements of that set and some elements in a different set, x and f of x. So the codomain is just the set where the outputs live. It could be bigger than the range, but it's just some set which contains all of the outputs. And then, yeah, as you said, the range is a subset of the codomain, which is all of the values it actually outputs. I think that's a good definition. Okay, some other short, how about, okay. How would you prove, this could be like one sentence, how do you prove that the empty set is a subset of any set A?
I believe that it can be shown to be a subset of any set because it would just have to be an element that, oh wait, no, I'm not quite wording this way. White, right.
White. You're wording it black. Let's start with the definition. What's the definition of subset?
This, oh god.
That one has to be in memory. I'm running out of space, unfortunately, but wow.
Okay, it's just all the a set of elements that I can't quite word this right.
Well, here, let's write it out together. So, if let me use different letters because A was already used in that problem. C subset of D means what? What is the formal definition of this statement that C is a subset?
Such that all elements of C are in D.
Yeah, so let me give a name for that. Let's be a little more precise. Means for all elements, I'll call the elements in C lowercase c. So if I'm writing this definition precisely, for all C in C, what is true?
C and D.
Yeah, C and D. Okay, so that's the definition. Now, we're trying to prove that the empty set is a subset of A. So to prove that this is true, what do I have to do? I have to show for all elements of the empty set, that element is also in A. What's the next line of the proof?
Since, let's word this right. Since the null set has no elements, that means that it can't be in A as long as A has elements.
Well, that's not quite true because even if A has no elements, it's true that the empty set is a subset of itself, right? So we don't have to use anything about A, we just have to use the definition of the empty set and this definition. So But I think you started with a good observation. So since the empty set has no elements, and what should we say? What does this statement mean, I guess, is a different way to think of this question. So to prove...
I guess since there are no... This is just me wording it slightly longer. There are no elements of the null set. Wait, no. That would just not work. Never mind.
It sounded like you almost said something. Where were you going to go with that?
I was going to say that there are no elements of the null set to be in A. So how can it be a subset? But that's not...
Well,
no.
You said something correct, but then you came to the wrong conclusion. You said there's no elements of the null set, and then you concluded that means that this definition is not satisfied. But it's the opposite. Because what does this definition mean? This means to check that C is a subset of D, I have to iterate. This is an existential quantifier, right? That means I have to look at every single element of C, and if that element of C is in D, good. If it's not, then the definition fails. So if I get to the end and I haven't failed, that means C is a subset of D. In the case of the empty set, there's no elements to check. So I automatically get to the end of this iterative procedure to check that every element of the empty set is in A. I get to the end of the procedure immediately because there's no elements to check. And since I've gotten to the end of the procedure, that means that it succeeded, right? There's no elements to check, so it is automatically true, right? Maybe a better way to write this definition is let's write this as a Python function. So I'm just going to rewrite what you just told me a moment ago as a Python function. So def I'll pretend these are lists. So def why am I writing it like this? Is subset, and it'll take in two things, C and D. Here, what does this function do? Well, for C in C, if C is not in D, so I found an element in C which is not in D, if that's the case, return false. It's not a subset. If I get to the end and everything was fine, then I return true. So just looking at this Python program, what flow executes if C has no elements? What does the interpreter do as it reads this?
And it skips over the for statement and returns true. So it is a subset.
Yeah, good. So that's why, I mean, maybe it's not the way that we would phrase it in a proof, but that's what's going on under the hood. So, okay, since the empty set has no elements, it is automatically true. This is sometimes written vacuously true. Do you remember this word? It was in the not the first reading assignment, it was in the second reading assignment. There was a little insert about this vacuous truth, and it had a statement about flying pigs or something, and you posted an annotation saying, I especially like this statement among the others because it's related to computer science or programming or something. You remember this?
Did I miss something?
Did you miss something? Did you miss the annotation comment, you mean?
I heard it, but I didn't hear it.
Ah, okay. I was just commenting on in the second reading. You posted an annotation on an insert in the AOPS reading about vacuously true, and you said you especially liked that statement. I don't know if you remember writing this.
I don't think I remember that.
Okay, that's fine. Okay. thoughts on this? Are you now prepared to write this proof yourself in the document, or do you want to talk through any steps?
I believe I understand this. I need to go shortly to go take care of chores if that doesn't bother you.
Okay, good. Yeah, should we quit here then?
I believe this is as good of a time as any. I don't
Sound very hesitant. Okay, yeah, let's quit now. If you have time to do the other challenges tonight, then that's good. And then next week, we'll finish the consolidation document. You'll present one day, and then we'll start limits. Sounds good.
Okay.